Hey guys, so this is the second video of molecular quantum mechanics, and this chapter 1 is like math and some new concepts about quantum mechanics. So this video will be only about the math I had to learn to basically understand the whole chapter, but I will record another video with just like only quantum mechanics concepts. So yeah, overall, like this was a really challenging chapter. I didn't know all the math I learned it. So like uh, integral over operators, I have no experience with that, so I had to learn with some YouTube videos and books. But yeah, like let's just start the talks here. First, they introduce us linear operators. We have like an operator operating two functions, like one function with some constant here, and if this is equals to the constant times the operator operating in the function f, then you can call this an linear operators. This is like multiplication. You can apply the multiplication operator in don't know, this 3 times 1 times x. This is equal to 1 times 3 times x. So this is a linear operator. Like integration is a linear operator also, but square root isn't a linear operator. So yeah, this was the easiest concept I learned it. And the second one is eigenvalues and eigenfunctions, which is like it seems like pretty important in quantum mechanics. So basically, f is an eigenfunction of an operator if satisfies this. Operator operating in a function is equals to a constant times f, and this constant is called the eigenvalue. So basically, this is it. Here is some representation about the position operator and the momentum operator. Okay, and here we can start with commutation, and if your operators a and b satisfies ab equals ba, and a and b commute. If they don't, they are non-commuter operators. So yeah, and this quantity ab minus ba, it's called the commutator. So I didn't knew that, but it's pretty simple, I think. And here is an important operator, the Hamiltonian operator. I had some experience with this in the chemistry Olympiad, so I already knew that, but this time we will go further in the math and probably will be getting harder and harder, but okay, let's face it. So for a particle in a one dimension, the Hamiltonian operator is, this is the kinetic energy, Vx is the potential energy. So we can open it with the momentum representation, and yeah, we could get this expression here. So these steps were all easy to understand. And for 3-dimension, we can use the Laplacian operator, which is all the partial derivatives of x, y, and z. Is the second partial derivatives of x, y, and z. So it's pretty common for me, I think. So this was not like a big deal. Yeah, this part was like not easy, but not hard. So I could understand the concepts very well in applying the exercises. So I forgot to mention that in the chapter 0 I had to do some exercise, and it was like okay. There was someone I didn't know how to solve, but then I Google it and understand. So it's pretty normal. There are some difficult exercise and some easier ones, and I didn't know how to solve all the problems, but yeah, I solved almost all the problems, but not all. So the chapter is a very introductive one. I probably won't be able to solve the majority of problems in chapter 1 because like there are some concepts here I didn't know, and I'm getting used to do math and some things like that. So we will see. Like I didn't try to solve them yet, but probably after this video I will start to try. And yeah, so this was the simple math, I think, in the chapter 1, and here is a little complicated math. So this is the energy for so I came up with an expression for the Hamiltonian operator with hydrogen or hydrogenoid atoms, because the energy of an electron in a hydrogen nucleo is this expression here. So like, just do the chapter 0 review, and we came with the Hamiltonian operator being this for electron in a hydrogen atom. And okay, I understand that. So we came with integral over operators, which is a very, I didn't know anything about it, so I had to learn, and it was very hard, I think. But okay, so this one here is like we are integrating from the entire space available to the system, x, y, and z in the 3 dimensions. So the entire space is like x being minus infinity and x to x being plus infinity. And okay, this was like I was a little bit scared about, but I could understand. And this is a pretty important integral, the normalization integral. That we pick the conjugate of a function times the function itself, and integrate from all over the space in these 3 dimensions, and this must be equals to 1. So yeah, there were some exercises in the book about it, and it seems to be very important. So I will sure check this up later. So we can, with the Dirac brackets notation, I already had seen this in high school, but didn't like push all the way to it. So here is some notation. This thing here, it's equals to an integral of an operator. This is the complex function, conjugate function, and operating and real function in the 3 dimensions. This thing here is called the bra, and this one the cat. So if we put all those two together, we can bracket. It's very very smart. So this is another notation for probably normalization integrals. We don't have to write this thing here. You just like bracket. We just can do this equals to 1, and this is a normalization integral. Very simple notation. And this one here is the Hermitian operators. They have some really cool properties. So we pick up two functions, and suppose this. If this is true, then they are Hermitian operators. And these are some consequences. They have eigenvalues. Their eigenvalues are real. And if you have eigenfunctions correspond to different eigenvalues of an Hermitian operator, then they are orthogonal, which means that this thing here is 0. So yeah, this is our pretty good consequence. Here it's a little bit of quantum mechanics, but I will explain this in the next video, because I think like it's better this way. We can do a math video, like chapter 1 math video and chapter 1 quantum mechanics concepts, probably. So yeah, this is it. So the chapter 1 was a little bit challenging. I like the chapter 2 must be like super hard. I think I will try my best to understand all of the things and do the stuff I need to do. And from the my research is doing well, I think. So today I had to calculate the energy in a really nanocage of oxygen and silicium, and their adsorption with CO2. Like, my computer was connected to the university cluster, so takes me like 2 hours to compute this. I will try to record some calculus I am doing my research and post it in the channel. So if you have any suggestions about like how can I improve my videos, and suggestions about doing quantum mechanics, studying quantum mechanics by myself now, before I'm going to do SF, leave in the comments, please. And yeah, so bye guys, hope to see you guys in the next video.